All right, good afternoon, class. So today we are continuing in chapter 5, where previously we've learned about the logarithm function and the exponential function. You have e raised to some power of x, or you have like the number 2 raised to the power x. So on and so forth. Those are all exponential functions when they follow that format with x and the power. So that's what we've done so far in chapter 5. Today we're going to go ahead and get through the rest of Chapter 5, so we're going to cover sections 5.3 and 5.4. And really, these last two sections here are going to finish up everything we've learned about derivatives. After today, you're going to know how to take the derivative of anything except for trigonometry, but that's not specifically required for this class, so don't worry about it. Beyond that, you're going to be able to take the derivative of anything you could possibly want, which is going to be great. And so let's get started. So the last derivative we haven't talked about is how to take the derivative of a logarithmic function and how to take the derivative of a exponential function, which both of which are rather simple, but it's just a matter of learning the rule and then getting some practice applying them, and then you should be good to go. So let's get started. So this afternoon, sorry. Well, my morning for you, whenever you're watching this. We are in section 5.3. We're in section 5.3. And is that showing up? Yeah, it is. Okay, cool. And this section, we're talking about logarithmic functions. Logarithmic functions. So what is a logarithmic function? Well, as we talked about in the previous lecture videos, f of x equal to the natural log of x, this is a natural logarithm. And so this is a logarithmic function. And the rule is actually fairly simple here. If you want to take the derivative, then f prime of x is equal to 1 divided by whatever's on the inside, whatever you're taking the natural log of. So in this case, it's just 1 over x. And that's it. This is the derivative rule for logarithms. And so what else can we do with this? Well, we can also take a step further, and suppose we have f of x, which is the natural log of, and it's got some function of x on the inside. Then in this case, we can actually apply the chain rule that we learned previously. What does the chain rule say? Well, it says you take the derivative of the outermost part first. So what's the derivative of the natural log? 1 divided by whatever's on the inside, g of x. And then the chain rule says once you've taken the derivative of the outside part, you multiply it by the derivative of the inside part. So what is that? That's just g prime of x. So anytime you're trying to take the derivative of a natural log that has some function of x on the inside, then it's going to work out to be the derivative of the inside part divided by the inside part. And that's going to be true every time. So a simple example of that, if we have f of x is equal to the natural log of, let's say, x squared plus 3, then what would the derivative be? Well, according to the chain rule, we take the derivative of the outside part, so it'd be 1 divided by the inside part, but we leave it alone at first, so x squared plus 3, and then we multiply it by the derivative of the inside part. And what's the derivative of x squared plus 3? Well, we just use our power rule here, and we're going to have 2x. So clean it all up, and we're left with 2x divided by x squared plus 3. And that's actually as simple as we can make it. That's your final answer in this case. So derivatives of natural logs really aren't so bad. They shouldn't scare you, it's just a different type of function and requires a different rule for finding your derivative. So not a big deal, not too much to work with. You just want to make sure that when you are working through these problems, you take your time. You don't want to rush through it and make a silly mistake. Just follow the methodology step by step and you're going to be fine. So again, that's 1 divided by the inside part times the derivative of the inside part. And that's going to be true for every natural log. Now, even in the case where if you've got like a 2 on the outside of some g of x here, well, we've already learned before that if you have 2 times some function of x, then the derivative is just 2 times f prime. So this constant, anytime you have a constant here on the outside, you can just ignore it and then multiply it against whatever your final answer is. So again, that's not such a big deal, just reusing rules we've already learned. Things you might want to watch out for: if you see the natural log of g of x, but then maybe it's got some other function on the outside, some h of x, then in this case, to find your derivative, you're going to have to use the product rule because it's a function times a function. So what would this be? Well, derivative of the left, that's h prime of x, times the right guy, so that's natural log of g of x, plus the left guy, h of x, times the derivative of the right guy. So the derivative of natural log of g of x is g prime of x divided by g of x. And so our final answer here is h prime of x times the natural log of g of x plus h of x times g prime of x divided by g of x. And in this case, that's as simple as you can get it because I've left h and g as arbitrary. So this is your final answer here. But if you knew what h and g were, then you could certainly plug them into this and find what the answer really is based on these functions. So again, nothing new here. We're just applying the same old rules we already knew, such as the product rule, the chain rule, so on and so forth. We're taking these rules and then we want to apply them to this new rule that we have for taking the derivative of a natural log. So that's all we've got there. So let's see. So that covers the notes for 5.3. So let's go ahead and take a look at what kind of examples you might be seeing in the Hawks Learning quizzes for this. Alright, so here we go. First example, suppose, oops, my marker's dying on me. Let me try, well, we'll try this one. Suppose f of x is equal to 18 times the square root of x times the natural log of 5 minus 11x squared. Now I really like this question because it's bringing together everything we've learned so far, or a lot of the stuff we've learned so far. So how do we take the derivative of this? Well, we've got a function of x, that's right here. I'll label that L for left. And then we've got this natural log on the right, so I'm going to label that for r. So we've got a function times a function, and so we have to use the product rule. L prime times r plus L times r prime. So here we go. We'll just take it one step at a time. So first, and actually, I'm going to rewrite this function where I've got the square root of x. I'm going to rewrite that as 18 times x to the 1/2 power, which is equivalent to the square root, but by writing it this way with the 1/2 power, it's a little bit easier to see how to apply the power rule here, since we're going to need it when we take the derivative. So I've got 18 times x to the 1/2 times the natural log of 5 minus 11x squared. So here we go. Derivative of the left guy, 1/2 comes down, 18 divided by 2 is 9. So 9 times x, power decreases by 1. 1/2 minus 1 is a negative 1/2, times the right guy, so times the natural log of 5 minus 11x squared, plus the left guy, 18x to the 1/2, times the derivative of the right guy. So again, just using this rule we have set up over here, that's going to be 1 divided by the inside part, so 5 minus 11x squared, times the derivative of this inside part, which is going to be a negative 22x, just using our power rule here on the inside. And that's it. So now that I've done this, all I got to do is clean it up a little bit. So this x to the negative power, I can move it to the denominator. So I'm going to have 9 natural log of 5 minus 11x squared divided by the square root of x. And then here, so I've got a positive 18 times a negative 22. I'm going to have a negative, and then 18 times 22. I believe that's going to give us a 396. 396. And then we've got x to the 1/2 times x to the first. When you're multiplying x's to different powers, you just take their powers and add them together. So 1/2 plus 1 is 3/2. So we have x to the 3/2 power divided by excuse me, divided by what we already had here, 5 minus 11x squared. And that's pretty much all we can do for simplifying here. That's our final answer. And it might look kind of big and ugly and whatever, but this is as simple as we can actually make it. We can't do anything else to try to cancel any of this stuff. And so this is a perfectly valid final answer. So don't let that scare you if you get a final answer that doesn't look very pretty. Other things you could do, I guess if you really wanted, you could move this 9 to the inside and have this raised to the 9th power. Because we have that rule where you have, if you have r times the natural log of x, then that's equal to the natural log of x raised to the r power. So you could move that 9 to the inside and raise this guy to the 9th power on the inside. But again, that's not really going to make anything cancel. It's not going to simplify anything. So at that point, it's just a matter of preference whether you want to leave the 9 on the outside or on the inside. Totally up to you. Both are perfectly valid answers. So don't stress over that. I'm just highlighting that you could do that if you really wanted to. But it's not a big deal, so I'm going to leave that up to your own discretion. So, there you have it. That's a good example that takes together a bunch of stuff we've talked about so far. Let's see what else we've got in section 5.3. Alright, so 5.3. What's another example? This one's good too. Alright, so let's suppose we have f of x is equal to 2x squared divided by the natural log of x to the 5th power. So we want to take the derivative here, and we notice we have a fraction. We have a function divided by a function, a top divided by a bottom. So in order to take our derivative here, we're going to need to use the quotient rule. So what is the quotient rule? So it's derivative of the top, so it's going to give us 4x times the bottom, that's natural log of x to the 5th, minus the top, 2x squared, times the derivative of the bottom, which is going to be 1 divided by x to the 5th, times the derivative of the inside part, which is going to be 5x to the 4th. And this is all divided by the denominator squared. Now it's important to recognize the difference here. When I have the natural log of x to the fifth, and then that whole thing is raised to the second power. This is not the same thing as if I had the square on the inside. I can't simplify this by pulling the 2 down to the outside. The rule that we had before was specifically if you have the natural log of x to the r, then this is r times the natural log of x. But notice the power that we pulled down, it's the power of the inside part. This square is not the power of the inside part, it's the power of this entire natural log. So you cannot pull this 2 down. Don't make that mistake, because that's often something that students do without thinking about it, and then it'll throw off your whole answer. So try to avoid doing that. With that being said, yes, if you wanted to, you could pull this 5 on the inside out as a coefficient on the natural log, but I mean, again, just as in the previous example, that's not really going to help us simplify anything. It's not going to help us cancel anything. So I'm just going to leave the power on the inside because it really doesn't matter. But we'll see that as we get to our final answer here. So our next step is actually to simplify the numerator sum. So we've got 4x natural log of x to the fifth. And then we've got 2 times a 5, that's going to be a 10. So we got a negative 10. We've got x squared times x to the fourth. So we're going to have x to the sixth in the numerator. And if you think about it over here, x to the sixth divided by x to the fifth, all the x's in the denominator are going to cancel. And it's going to leave us with a single x in the numerator. So we're actually going to have a negative 10x after we finish multiplying all of this out up here. And then we just divide by the natural log of x to the fifth quantity squared. And there you have it. This is our final answer. And again, just like in the previous example, yes, this might not be the prettiest fraction in the world, but this is a perfectly valid answer. We can't really do much else to simplify it. Well, with that being said, I suppose if you really wanted to, and I don't think it would make too much of a difference, if you really wanted to, you could take this denominator and divide it into both terms of the numerator separated by this negative. And if you were to do that, you would cancel one of these natural logs in the top, and we would have 4x divided by the natural log of x to the fifth. It would be to the first power since it canceled with one of them on the left. But then on the right, we would still have 10x divided by the natural log of x to the fifth squared. And then again, that's as simple as we can get it. We can't really cancel it any further. Yeah. So either of those answers are perfectly valid. I personally like to keep it written as a single fraction rather than have a fraction minus a fraction. But again, that's totally up to you. You can write it either way. Both answers are correct. And I'll accept either for homeworks and such. So there you go. There's another good example, pulling together a bunch of stuff we've previously learned. All right. What else have we got? Let's see. So this last example is actually a word problem. And this will be the last example we'll look at for 5.3 before we move on to 5.4. So, here we go. So the question says, aphids are discovered in a banana orchard. The Department of Agriculture has determined that the populations of aphids T hours after the orchard has been sprayed is approximated by, so they give us an equation here, N of T is equal to 1800 minus 4t natural log of 0.13t minus t. And they also tell us that t is bounded by 0 and 100. So aphids, if you're not familiar, they're a type of bug. In particular, they're a rather destructive bug that eat a lot of produce plants. So in this banana orchard, the aphids are ruining the crop, and so this is bad. The farmers don't like that. So the Department of Agriculture is planning to spray the orchard to kill the aphids, and they have this equation to approximate how many aphids are going to be left still alive after T hours have passed since they initially sprayed the orchard. So this is an approximation for how many will be left as time goes on, and this number will eventually go to 0 since they'll eventually be killed off by the spray. Or at least that's the hope. So what's the question here? The question is, what is the maximum number of aphids in the banana orchard? In other words, maybe they're trying to find out, okay, we know we've sprayed them, and we know they're going to die eventually, but we want to know how large is their population going to get before the spray actually finishes them off. So this could be important for if you're trying to determine, okay, I've just sprayed my crops, but how much damage am I going to take before they actually die? In order to know that, you're going to have to know how many aphids survive, or how long they survive, and you're also going to want to know how large does the population get? What is the worst case scenario? How many aphids will there be at their maximum peak before they start to die off? So that's the point of this question here. However you look at it, if we're trying to find a maximum number for this n is number of aphids, then to find a max, we need critical points. So we have to take the first derivative. So here we go. We're looking for n prime of t. The derivative of 1800 is 0. Then we come to this bit here in the middle, negative 4t natural log of 0.13 t. So we have a function of t times the natural log with a function of t. So we're actually going to have to do the product rule. So here we go. Derivative of the left guy is going to be negative 4 times the right guy, so natural log of 0.13 t. Well, it would be plus, but when I write the left guy with a negative sign, it's going to make it negative. So we've got minus the left one, 4t, times the derivative of the right one. So we have the derivative of the natural log, so we're going to have times 1 divided by 0.13 t times the derivative of the inside part, which is just 0.13. And then on the very end, the derivative of minus t is minus 1. So there we go. We have our derivative written out, but now we need to clean this up a little bit, and we need to find out where it equals 0. So here we go. So for this left one, it's already pretty simplified. We've got negative 4 natural log of 0.13 t. Now here on the right, lucky for us, this 0.13 is going to cancel with the 0.13 in the denominator, so that's nice. And then the t and this t are actually going to cancel since one is above and one is below. So for this middle term right here, we're actually going to be left with negative 4 and then minus 1 on the end. So that cleaned up very nicely. And then, so we've got negative 4 times the natural log of 0.13 t. And then negative 4 minus 1, that's just negative 5. And that's it. This is our first derivative. This is n prime of t. Now remember, what are critical points? Critical points are where the first derivative are either 0 or undefined. So especially when we're talking about natural logs, you want to be thinking about, okay, where would this function be undefined? Because remember, for the natural log, we can only plug in positive numbers. If you try to plug in a 0, or if you plug in any negative number, well, it doesn't exist, so it would be undefined. So in this case, if we plug in t equals 0, and notice we can do that because 0 is included in the bound here, then if we include 0, then we're going to have the natural log of 0, which is negative infinity. The derivative is undefined there. So this is one critical point. Okay, so far so good. But now we want to know, okay, where does this function equal 0? For what t does this equal 0? So we set it equal to 0, and I'm going to add 5 over, and then divide by -4. So I've got the natural log of 0.13t is equal to -5/4. Okay, so far so good. Now what? Well, now we want to get t alone by itself, but currently t is wrapped inside of a natural log function. This is where we take advantage of the fact where, as we learned in the previous lectures, the natural log has an implied base e, and so we can rewrite this equation by taking the base, raising it to the power it's equal to, and then set it equal to what's on the inside part. So what we actually have here is e to the -5/4 power is equal to 0.13t. And there we have it. So what does this do for us? Well, now I can divide by 0.13, and I'm going to get t all by itself. So I've got e raised to the -5/4 power divided by 0.13. And that is a perfectly valid answer. Some things to be wary of. Sometimes you may be tempted to, let's see, where to put my calculator? Give me 1 second. I'll be right back. Okay, I'm back. So what I was discussing here was oftentimes students are tempted to go ahead and take this number and put it in your calculator. So you'll have e raised to the -5/4 power, and then you divide it by 0.13, and this is approximately equal to 2.20. And then students will take this number and say, oh, it's just 2.2. And in reality, and when you look at the calculator, there's a long string of numbers after this. And so when you try to simplify this and you round it off like this, you actually get a huge margin of error. And it's going to throw off your answers later down the road, and then you're going to get the wrong answer, all because you just tried to write it as a decimal instead. But you cannot do this because e, like the number pi, is an infinite number. It's infinitely long is what I mean. And so you can't simplify this into some regular looking number because this e, its decimals continue on forever. So you actually want to keep this e for the sake of accuracy so that when you plug it in later to find other numbers, you're going to have a more accurate number. And in fact, it's going to give you a better answer than 2.2. And so if you're taking a certified quiz or if you're doing a homework assignment for me, if you simplify like this and you plug this number in, it will be wrong and you will lose points for that. So watch out for that. Don't make that mistake. But with all that being said, it is useful to at least know what this decimal looks like so that you can check the first derivative test. So what are our critical points? Well, on the far left, we've got 0, which is the smallest number we can plug in based on our bound. So we've got 0, and then we've got this 2.2 number. It's not really 2.2, but just for the sake of approximating and trying to fill in this first derivative line, then it's going to work for us. So if I plug in, say, 1, that's a number in between these two guys. Then for my first derivative, I'm going to have the natural log of 0.13 times -4. So natural log of 0.13 times -4. I get a positive 8.16. And then when you minus 5, it's still positive. So we've got a positive in between here. So right off the bat, this tells us 0 is not going to be our guy for the maximum aphid population. Why? Because from 0 to 2.2, the population is still increasing. So the population at 2.2 is higher than it is at 0. So 0 will not be our final answer. Okay, so 2.2 is a candidate. We're increasing on the left, but what happens on the right? So I'm just going to plug in another easy number, say 3. That's bigger than 2.2. So 3 times 0.13 is 0.39. I'm going to take the natural log of it. Then I'm going to multiply it by a negative 4. And then I'm going to subtract 5. And here I actually get negative 1.2. So I'm negative to the right of this critical point. Now this is great news. This means 2.2 is a local max because it increases and then decreases. So 2.2 is our local max, and now to get our final answer, all we have to do is go back up to our original function and plug it in. And when you do this step, you want to make sure that you use this number you have with e in it, because this is going to give you the most accuracy for finding the number of aphids. Now, I'm running out of space here. We're also running out of time. So I'm just going to tell you that if you plug in this number into this formula for n of t, then you're going to get about 1809 if you round up. And so after about 2.2 hours, there are going to still be 1,809 aphids alive. After that, they'll start to drop off again, but that's the maximum population reached after the banana orchard has been sprayed. So there's your final answer there. So with that being said, let's go ahead and switch gears to 5.4. 5.4. All right, 5.4. So we've talked about how to take derivatives of logarithmic functions. But now, as we did in 5.1 and 5.2, we want to talk about what about exponential functions. So now we want to talk about exponential functions. All right. So what is an exponential function? Well, that was when we had f of x is equal to e to the x power. And so this is an exponential function. We saw that these functions were especially useful when you're trying to determine interest for bank accounts, compounded interest, compounded continuously, so on and so forth. That's what these are really useful for in terms of banking. But whenever you want to take a derivative of an exponential function, well, it's actually quite easy on us. F prime of x in this case is just e to the x. So e to the x is really this weird function where when you take the derivative of it, you end up getting the same guy. Why is that? Well, if we think about it, if we have y is equal to e to the x, and I want to find out what is the derivative here, well, I can take the natural log of both sides. So I've got the natural log of y is equal to the natural log of e, but then I can bring the x down. Natural log of e is just 1, so I've got the natural log of y is equal to x. And now, if I try to take the derivative, then oh, you know what? I'm actually leading you down a rabbit hole for something you guys haven't learned yet. Yeah, so scratch that. Yeah, forget what I was saying there. There are reasons that the derivative is just itself, but we haven't covered that kind of stuff yet. And I'm actually not sure if we will for this course, since this is strictly a calculus for non-math and science majors. So I won't go too heavily into the why this is true. Just take my word for it that the derivative of f of x, when f of x is e to the x, is just e to the x. It doesn't change. But what does this mean for us? Well, this also means that if we think about it with regard to the chain rule, suppose we have a function that is e raised to the power of some function of x. Well, by the chain rule, we say, okay, go ahead and take the derivative of the outermost part. The outermost part is this e raised to this power, so we'll just leave it alone for starters, and that's just e raised to the g of x power. But then, by the chain rule, we have to multiply it by the derivative of the inside part. What's the inside part? It's this g of x, so the derivative is g prime of x. So your final answer in this case is going to be e to the g of x times g prime of x. So what will that actually look like? Well, suppose f of x is equal to e to the 2x. Then f prime of x is going to be e raised to the 2x power. We leave it alone to start with. And then we multiply our function by the derivative of the inside part. The derivative of 2x is 2. And so our final answer is 2 times e raised to the 2x. And that's it. There's your final answer. So again, just as we saw in 5.3, the rule we use to take derivatives of exponential functions are really quite simple, but we're then going to take these rules that we've just learned, apply old rules we already know, such as the chain rule, and then we'll use them together with everything else, the product rule, quotient rule, so on and so forth. All this stuff is going to come back together. So you want to make sure you keep track of all these rules. You want to make sure you apply all of them correctly when they're warranted. And you want to make sure you take your time and do this step by step so you don't make a silly mistake skipping over something simple. All right, so far so good. So let's see what we've got next. So for 5.4, yeah, we're ready to start jumping into some examples. So this first one is f of x is equal to 2x cubed times e raised to the 2x plus 1 power. So notice I've got a function of x on the outside as a coefficient being multiplied on e, and then I've got e raised to some power. So I've got two functions of x. I have a left function times a right function, and so I'm going to need to use the product rule again. So f prime of x is going to be the derivative of the left, which is 6x times the right, e to the 2x plus 1, plus the left, which is 2x cubed, times the derivative of the right. So the derivative of e to the 2x plus 1 is just e to the 2x plus 1, but then we multiply it by the derivative of the power, so that's going to be times 2. And so our final answer is going to be 6x e to the 2x plus 1 plus 2 times 2 is 4x cubed e to the 2x plus 1. And there you have it. There's our first derivative. And so this is perfectly a valid answer. If you really wanted to, you could try to simplify this a little bit. If you wanted to factor out a 2 and maybe you want to factor out an x, and then you want to factor out this e to the 2x plus 1, then you're going to be left with on the inside, this is going to be times 3, plus this is going to be 2x squared. So you got to do that right. 3 times 2 is 6. That'd be 6x e to the 2x plus 1. Good. 2 times 2 is 4. X squared times x is x cubed. That'd be 4x cubed times e to the 2x plus 1. There you go. So maybe you could argue that this is a simpler version, but really, I would accept either of these. I don't think one is necessarily better than the other. But they're both correct, and I'll accept either one of them for homework assignments and such. So there you go. There's an application of the product rule with the exponential function. All right, and let's see. Let's go ahead and do just one more example. So let's see. Let's see if we can pick another word problem just to give you a taste for what you might have to work with. So here we go. The population of an unknown bacteria in an experimental culture is estimated by the population function. So they're giving us a function to estimate how many bacteria cells are alive in this culture based on time, x. So this equation is 10,900 divided by 1 plus 49 times e raised to the negative 0.1 x. And this is where x is the number of hours after the experiment begins. How fast is the population changing? So when you see this question, they're asking for how is something changing? What is the rate of change? They're asking for what is the first derivative? So how fast is the population changing at the end of 3 hours? So what are they asking for? They're asking us to find n prime of 3. They just didn't say that specifically. And they want us to round our answer to the nearest integer. Okay, here we go. So we need a derivative, but first I'm going to rewrite this equation by taking this denominator, raising it to the top with a negative 1 power. And I'm doing this just because it's going to make things easier on me because now I don't have a fraction, and I can just apply my good old chain rule. So what does the chain rule say? It says take the derivative of the outermost part first and then multiply it by the derivative of the inside part. So here, this is our inside part, so we're just going to leave it alone to start with. And I've got this raised to the negative 1 power. Well, by the power rule, when I take the derivative of this, the negative 1 comes to the outside. So I've got negative 10,900 times 1 plus 49 e to the negative 0.1 x, leave the inside alone to start with, raise it to the negative 2 power, and then multiply it by the derivative of the inside part. So I'm going to have times 49, I can just leave this constant on the outside, no big deal, e raised to the negative 0.1 power of x, negative 0.1x, but then I got to multiply it again, so I've got a chain rule within a chain rule. I've got to multiply this by the derivative, negative 0.1x. So that's negative 0.1. Okay, so what does this do for us? Well, let's start by getting all of our coefficients on the outside, which I just boxed in there. So we've got negative 10,900 times 49 times a negative 0.1. So a negative times a negative, my answer is going to be positive. And when you multiply this out, you're actually going to have 5,300, 410. We still have our e raised to the negative 0.1 power. And then this is all divided by 1 plus 49 e raised to the negative 0.1 x squared. And there you have it. That is the second derivative. And so the last and final step is to take 3, plug it in for x, and get your answer. And for the sake of time, I'm just going to tell you that if you plug in 3, then you're going to get about 28. So there are 28 bacteria that are multiplying, that are reproducing per hour. And there's your final answer for this question. So there you go. So that covers everything that I wanted to talk about in 5.3. Of course, if you have any questions, concerns, if anything didn't really quite make sense during this lecture, of course, let me know, email me, we can talk about it. There's also the option of bringing your questions to the Q&A session later in the day, and we'll also talk about it there. Otherwise, that's everything I've got for you today. So with that, I wish you the best of luck.